Okay, so today we will start this new topic on optical model. Now, before I proceed, let me give you some motivation of what was the actual need for this model. We will talk about this on several occasions during the course. Okay, now you see, it is important to consider cross sections. Now this time cross sections which are averaged over energy ranges. However, these energy ranges are greater than the average, greater than your average resonance energy, basically the resonance spacing. Now we haven't talked about this issue, but right now let me concentrate on this. So what I want to do, I want to study cross sections which are averaged over energy ranges. Now these energy ranges are greater than the average resonance spacing. Now it is observed that if we do this, then at such energies the characteristic features, then from this study basically we observe that the characteristic features of a particular compound nucleus are suppressed, and features common to all nuclei are revealed. So this means that this type of study, that is cross section averaged over energy ranges which are greater than average resonance spacing, so it basically gives me a global study of nucleus, of nuclei, right? Now you see, it turns out that these averaged cross sections actually vary very smoothly with projectile energy while passing from one nucleus to neighboring one. This is very interesting. See, normally we have studied that when we go from one nucleus to other, the levels, energy spacing, everything changes. But when we study these averaged cross sections, then we observe a sort of smooth varying over energy. Now as the incident energy is varied, actually we observe broad resonances. Let me show you some of the data, that will be better. Okay, see for example here, what you are seeing is basically the smooth variation of cross section. So basically you see a smooth variation. Of the cross section. This is the cross section, along with this is neutron energy, and this is the atomic weight. You see an overall very smooth cross section, and this result that you are seeing, basically let me show you a different one here. Here you can see the smoother cross section behavior much better in the figure B, the lower figure. Now these results are basically shown for, basically these are the results for neutron interaction with elements which are heavier than manganese as a function of the neutron energy and the target nucleon mass. So this atomic weight is basically corresponds to the target Okay, now you see these cross sections, these ones, you see these smooth variations, you see more or less smooth variation here also, overall a smooth variation. Okay, so basically these variations are observed. So see, this is my plot. One way is the sigma, another axis is your atomic weight, and then we have got the neutron energy, and this corresponds to the target. So this is the overall scenario. Now you see these overall cross sections, basically they appear to be related to the bulk properties of the nucleus. Global overall bulk properties. Nucleus, and such that the details of individual structure become unimportant. This is the meaning of bulk properties, right? Now this remarkable feature of this nuclear cross section for neutrons, it can be actually explained by optical model. This is the feature. So this can be explained very nicely by your optical model, where basically
optical model
yes,
कुछ optical model है जो इनका प्रयोजनीयता बोलन उनका आरेख बोलन.
What I am saying is that, you see, if we consider the cross sections which are averaged over energy ranges that are greater than your average resonance spacing, then we observe a very smooth behavior of cross section. I shown you, and these features, there the individual structure becomes unimportant. We are observing a global feature, bulk property of the nucleus, and this will be explained by your optical model. Okay, so I just told you that here basically we will be using a complex potential. Now what happens is that in optical model I will be writing OM for short. Basically we will be considering certain assumptions. The first thing we will do is we will assume that all individual nucleon interactions between the projectile and target nucleus can be replaced by a one body potential or one body interaction that can be represented by your potential VR. Now, don't you think this assumption is very much similar to the one that we have considered in the shell model? See, what we are doing here is I am assuming that suppose this is the projectile, okay, and this is my target, the two systems. Now let me draw. So inside them there are various nucleons. Good, a representation basically. Now when they will come close to each other within the range of the nuclear field, when they will come within the range of the, so suppose this is within the range of the nuclear field. Say for example, the whole stuff, this yellow color represents the nuclear field. Now the two of them are within the range of the nuclear field. Now what happens is that, see, we can have individual interactions, isn't it? Say interaction of this nucleon with this, interaction of this nucleon with this one, this nucleon with this one, same this nucleon with this one, and so on and so forth. We can have so many types of interactions. This is the real world. This is the microscopic picture. This is what is actually happening. Right. Now, instead of considering this such a complex problem, the first thing we do is we assume this thing. All individual nucleon interaction between this projectile and target, we replace it by just using the one body potential. Okay, so this is very important to understand. Now, so as I was telling, this thing, this assumption, this optical model assumption is very similar to your shell model assumption. And what did we do? How? So basically in shell model also we consider the nucleons. Remember what we do? If this is the entire nucleus, individual nucleons, we consider the entire Hamiltonian is broken down into two terms, H0 plus this small hi. H0 is the one body term, mean field part, where we assume that the entire potential is due to a nucleon is basically moving in the potential created by all of them together. This corresponds to your mean field H0, and the residual part is basically the correlation effect, the various nucleon effects. Now normally we consider only this part in single particle shell model, where we neglect this HI, residual interaction part. Anyway, so you see, you understand these things we have already talked about in this shell model class. Okay, so now again let us come back to the optical model. So basically this potential VR, this is the optical model potential, the VR potential, you can see this basically is expected to be uniform in the interior and falls off exponentially towards the surface following the nuclear matter distribution. Of course, outside the nucleus it is zero because of short range of nuclear forces. Now you see, a real potential alone is inadequate to describe the experimental data. Why? Because besides the scattering, absorption will also be present by the incident particles. Okay, let me show you a picture, a draw, let us. So suppose this is where is it now? Yeah, so this is my target and this is the projectile coming in, projectile coming, and there are lots of target nuclei inside this target, thick target. Now what will happen is that as a result of the interaction, there will be some interaction here, right? Some interaction, and then the target will pass. So suppose the intensity, initial intensity is say I0, and after some time, after the interaction, the forward intensity here, the undeflected beam, this is the undeflected beam. Suppose its intensity is say I final, say for example. Now what do you think about the values of this? Of course, I0 will be greater than I final. Why? Say for example, let me consider some examples. Suppose 1000 projectiles, they are incoming, okay, and here you are observing say 900 in projectiles that have actually gone through the target without some interaction. So what about the rest of the 100 projectiles? What has happened to them? Now out of the rest of 100, some will go shape elastic scattering. Understand? Shape elastic scattering, or basically your normal elastic scattering. Say 30 has got shape elastic scattering. So this is what I mean by scattering. And rest, what will happen to them? Rest will be absorbed, and then there will be a nuclear reaction. So basically nuclear reaction, and what is the rest amount? It is around 70, and this nuclear reaction can be your compound nuclear reaction depending on the energy of the projectile and various other things as well. It can be a direct reaction, or it can be a pre-compound nuclear reaction. So CNR, compound nuclear reaction, direct reaction, pre-compound nuclear reaction. See, so this is what I mean. Now when I am saying scattering, this I mean by shape elastic scattering, and this nuclear reaction, what I mean is basically your absorption, right? So you see, what I am saying is stressing on the fact that a real potential is not adequate to describe the experimental data. Why? Because in the case of experiment, along with this scattering, your absorption or the nuclear reaction part is also present, where the incident particles, see, in this case the incident particles is removed from this beam. Here also, in this case of shape elastic scattering, this is also removed from the beam. Now we are basically interested in the study of these 100 nuclei, which we are seeing that 30 has undergone elastic scattering and the rest has undergone nuclear reaction or absorption. So this is basically your absorption effect. Now you see, we already know that the scattering and absorption of light can be successfully explained, and that too mathematically, by using a complex potential. And so what we are going to do, we are going to use this complex potential for our nuclear physics case. So basically scattering of matter wave, our nuclear physics case, projectile and target, right? So projectile, target, scattering of matter waves, you can think of like that. And so just like light, we will be using a complex potential. Okay, so let us proceed. So let us consider a one-dimensional model with a wave incident on a square well potential. So what is this potential? What does this look like? So the potential looks like this. See the imaginary part. This is for z less than equal to capital R, and this is equal to 0 for Z greater than R. Okay. Now the energy of the nucleon outside the nucleus, so energy of nucleon outside nucleus is E, capital E, and so the wave number K is by H cross. Now you see, as the nuclear potential is attractive, the particle moves more rapidly inside the nucleus, so that its wave number actually becomes K plus K1 plus half I. This is capital K, and this is equal to you see, this is a complex wave number. Why? Because our potential is complex, and also you observe that this half factor is introduced to make the absorption coefficient. This is your absorption coefficient. So half factor is introduced so that this absorption coefficient becomes equal to the reciprocal of the mean free path of nucleon in the nuclear matter. Let me write it down. I will show it to you later on. So this is the wave number outside the nucleon, and this is the wave number inside the potential. What I am saying? So yes, as I was telling you, this half factor is introduced so that the absorption coefficient K becomes equal to the reciprocal of the mean free path of nucleon in the nuclear matter. Now, just like in optics, we can define the refractive index. So, refractive index N as the ratio of particle velocity inside and outside the potential. So, basically, what we have is this. And so from here I am getting your, this is small k, this is your capital K divided by twice small k. Okay. Now at energies where this is again small k, K into R is much greater than 1. Here K1 is much smaller than K, and also your capital K is again much smaller than K. So this means that N is approximately equal to 1, and we can write N square minus 1 approximately equal to twice N minus 1. Now, if we consider this relation and also this relation, and then we equate the real and imaginary components, then we have U is equal to H cross nu small k1, and W is equal to H cross by 2 mu k. Okay, where the velocity V, sorry, this is actually not nu, this is velocity. not new. And this velocity v is basically your old relation 2e by m, classical expression. So basically velocity of incident nucleon. Now the wave function, what about it inside the nucleus? So let me write it down. So wave function inside nucleus is given by basically this. Now let me break it into two components, k plus k1z again into e to the power minus half capital Kz. See, I have broken it into two components. So what does this mean? This means that from this expression, you see, there is I here, there is no I here. From this expression you can say that the nucleon wave is attenuated exponentially according to your, see, half and half, it will become 1, so minus kz. And this expression implies that the imaginary potential removes particle from elastic channel. So this expression implies that your imaginary potential removes particles from the elastic channel. Any questions? Now look very carefully to this expression. W is equal to h cross by 2 V into capital K. So basically this means that your K is clearly the reciprocal of mean free path in nuclear matter. And you see the product Vk is equal to V by lambda. This basically represents the number of collisions per unit time or collision frequency basically of incident nucleon with the nucleons of target nucleus. Now suppose rho be the nuclear density, then the number of nucleons per unit volume, and so basically this is the target or target nucleon density. Now I will basically write an expression. So let sigma be the average nucleon cross section in nuclear matter. Then we have from this relation K is equal to 1 by lambda is equal to rho into sigma, and so this is basically 3 sigma by 4 by 3 R0 cube. How? Because remember the fact that rho is equal to basically A by V, and the nuclear radius R is r0 a to the power 1/3. Okay, so this is the expression for K. So now, this is the second part of our topic discussion on optical models. So here we are going to derive expressions for the reaction as well as elastic cross section when a high energy neutron interacts with a nucleus of radius r. Now you can see in this schematic figure over here, you see this basically represents the path of a high energy neutron within a nucleus. So this is your high energy neutron. See? Okay. So what we basically observe is that the portion of the wave that strikes a distance b, so this is the distance b from the line, this is the line through the center of the sphere. So this b is basically, you can say, the impact parameter, right? Now this wave basically emerges after traveling a distance twice s. So this high energy neutron, so the wave emerges after traveling a distance 2s. Where a square is, from this expression, this is a right angle triangle, so a square is equal to r square minus b square, and after emerging this has an amplitude which is, let me denote by small a, e to the power minus capital K plus twice I K1 into S. Okay. So we can write the scattering cross section. So using this amplitude I can estimate the reaction cross section over here. This we have obtained previously. So this is integration 0 to r1 minus a square into the impact parameter b dB, and this is the overall result. So you must remember what we have obtained previously. So basically your nucleon wave function inside the nucleus, what was it? Basically psi equal to e to the power I n k z, right? This we wrote in separating two forms, k plus k1z into e to the power minus half capital K z. So this means that the wave, now in this figure if you see, so basically we can say that the wave transmitted through a distance z in the nucleus is given by how much? This is the transmitted. So this is e to the power minus capital K by 2 plus I K1 Z into e to the power I K Z, and this is basically your A into e to the power I K Z. Okay, so with this information we can, similar to our estimation of reaction cross section sigma r, we have now estimated the scattering cross section sigma t. sigma s, sorry, scattering cross section. See, this is the expression. Basically I am using the result from partial wave analysis also. Now both these expressions, this reaction cross section and the scattering cross section, actually reproduce the experimental data at high energies. So what I was saying is that these obtained expressions for sigma reaction and sigma scattering, they basically reproduce the experimental data quite nicely, or you can say accurately, at high energies. Now if we look into the structure of sigma r and sigma s, look into the structure, you see that this sigma r is basically a function of, you see, kr alone. See, this sigma r is, or you can say, just a second, yeah, let me write like this: sigma r divided by your pi r square. Yes, this term goes in. Then this entire thing is a function of kr alone. Whereas here, look, this by kr square depends on this k1 by k. Okay. So sigma scattering by pi r square, it depends on k1 by k. On k1 by k, along with that dependence is also there, and also your kr, both kr and this. So these are the differences. Well, let's proceed forward. Okay, so direct confirmation of theory, and that also independent of parameters, is obtained by plotting the sigma total, which is experiment, divided by a to the power 2 by 3, and this versus a to the power 1 by 3. This plot we have to do, and when doing this plot we find that the experimental points, all the experimental points from lithium to uranium, they lie on a smooth curve which reaches a maximum and then comes down as predicted by theory. However, these curves would be a horizontal line if the nucleus was a totally black sphere. that is complete absorption. Okay, complete absorption.
এটা বলুন আরেকবার।
আমি বলছি যে experimentally we find if we do this plot, we observe a smooth curve which reaches a maximum and then the curve slowly comes down as predicted by the theory. I will show you the theoretical results. Now these curves will be a horizontal line if the nucleus was a completely black sphere. That means if the nucleus would have complete absorption. Now this is not observed. This is not observed. Nucleus. So this means we don't observe this. So this means that the nucleus is not a totally black sphere. Let me show you the theoretical results now. So these are, you can see on the screen, these are basically the theoretical curves for small k1 by capital K equal to 1.5. Right. Now for this k1 and k for a given value, we can find the radius r as well. Suppose let us consider a value of k to be 2.22 into 10 to the power 12 centimeter inverse. Then this basically corresponds to a mean free path in nuclear matter of 4.5 Fermi meter, and the radius calculated from the measured cross sections, this one radius calculations, they basically yield R0 approximately 1.37 Fermi meter, and the associated value of say 3.3 into 10 to the power 12 centimeter square basically corresponds to the potential of depth 30.8 MeV. I am just giving you some number estimations. Okay, so now let me again start optical model after some break. So now you see the quantum mechanical nuclear interactions. Basically this we have described in terms of the potential VR when the projectile faces the target. This is the projectile and this is the target. Now you remember that while describing the elastic scattering, we assume that the potential changes the phase of the outgoing partial wave. Now I am talking in terms of partial wave analysis. So while doing the partial wave analysis, we assume that basically while describing the elastic scattering, we assume that the potential, it changes the phase of the outgoing partial wave without any loss of the incident flux, and the incident flux was only redistributed. So basically what I am saying is, if this is my incident flux, this is my outgoing flux, so what I am saying is that it was only redistributed in the case of elastic scattering. That means if thousands projectiles are going, say here in the undeflected beam we have got 900, then say rest of the 100 are deflected, and basically this undeflected plus deflected rest of the 100 without the change in the species, they basically mean that the incident flux was basically what? Redistributed. Now, in the case of nuclear reaction, what happens is that a part of the incident flux is lost. So, if this is a nuclear reaction, then what will happen is that suppose now 30 undergo elastic scattering and rest of the 70 they are first absorbed inside the target, and then they later on are the result we get as a result we get various nuclear reactions where the particles or the excited gamma rays can be emitted. So this is the result of the nuclear reaction, which is happening because of the 70 projectiles undergoing 70 nuclear reactions. Understand? Now, so here we have got both elastic, blue, as well as nuclear reaction, which basically happens after the beam was absorbed. So basically we have got number 1, redistributed flux plus absorbed flux. Okay, now one way of including this reduction of the incident flux is by multiplying the amplitude of each of the partial wave by a factor eta L. Remember, where eta L was less than 1. Now basically it was Feshbach and co-workers who suggested an alternative way of describing this absorption of incident flux, and this alternative way was to make VR complex. Okay, so this is the basic idea. One way we can describe the flux or reaction part using the partial wave analysis eta L less than 1. Another way is your optical model. This is the birth of the optical model. So now our nuclear potential basically becomes complex, and so we can write V total R is equal to VR plus say IWR, where this V total basically denotes the complex potential with real part VR and imaginary part WR. Now the effect of including the imaginary part is that the incident wave penetrates into the nuclear region as an exponentially decaying wave. Remember, in our last class we found this relation. See in the last class we found this relation. Okay, so basically this means that the imaginary part, its effect will be that the incident wave penetrates deep into the nuclear interior as an exponentially decaying wave, and so the nucleus behaves basically as a translucent body. So the nucleus behaves like a translucent body, and the interaction of the incident wave and the target nucleus may be compared with the interaction of a light beam with a crystal ball, and that's why we have given the name optical model. Now you see, a general optical model has 5 important terms. 5 terms. So let me write down those 5 terms. See, this is the general optical model potential, and here you can see 5 different terms. Now the first term I have written like this. So this is basically your first term over here. VR equal to minus V into this F R, function of small r, capital R and A. You can see over here. And basically, what is V over here? V is basically the depth of real part of potential, and this F RFA is basically the wood section form factor, where this R is the radius of, again, the real potential, and small a is the diffusiveness parameter. Okay. So now it's time to talk about the imaginary parts. And basically, so this was the VR. Now I am talking about this VL and VD components here. These two are basically constitute the imaginary part of the potential. So, imaginary parts. Of the potential, where this W and WD are depths of imaginary potentials having R1 and A1 corresponding radius and diffusiveness. Now you see, there are two imaginary potentials, right? Now these two imaginary terms, you see, are complementary of each other to the extent that this VL becomes important for high energy incident particles which may travel deep inside the nucleus and may give rise to absorption. So this is important.
Sir,
So again, just a second, yes. So this is the wood section form, right? Now again you see the imaginary part, we have just got this W and IWD, IW and IWD, two terms over here, and then the rest is, you see, the F, that is wood section form is there. So here we have wood section form, and here we have a differentiation part of the wood section form. Why is this term here? I will tell you later on. Just a second. Now, what I was talking about is this. You see, W and WD are depths of the imaginary part, R1, A1 as the corresponding radius and diffusiveness. Okay, so the imaginary part. Now, what I am saying is that this W1 becomes important for high energy incident particles. Because they can travel deep inside the nucleus, okay, and as a result they can give rise to absorption. In the entire volume of the target nucleus. So entire volume, this is important. Now you see VD, this one, the second part here, basically where will this be high? This basically will be high at the nuclear surface and is important for lower energies. So lower energy projectile, which gives rise to surface absorption. So this gives rise to volume absorption and this gives rise to surface absorption. See the difference? Why we have got two terms, two imaginary terms. One gives rise to volume absorption, another which is a surface term, basically because of the differentiation, its value is large near the surface, it gives rise to, basically this takes care of the surface absorption. Next, so we have talked about 1, 2 and 3. So this was real, CR, and next these two are imaginary. What about this VS? Fourth term. Well, now you see this fourth term is basically the spin orbit term. Okay, you see the L dot S term, S dot L, it is written like this, and this basically considers the polarization effects. Now you see a beam which is initially unpolarized, that is, it contains particles with randomly oriented spin. It gets partially polarized after your interaction with the nucleus target, and this effect is taken care by this term. Again, so I am saying is a beam of projectile which is initially unpolarized, after your interaction with the target itself, it can get partially polarized as a result of mainly the surface interaction. See, DFDR, the term over here. So basically surface effect is there, and so we have got this spin orbit term. And see, this is the last term, the fifth term, which is basically a Coulomb term. Now it has different values, of course, inside and outside the Coulomb radius of the nucleus, right, which is RC, the Coulomb radius of the nucleus. So this is basically what the empirical optical model is all about. 5 different potentials. Out of these 5, which ones are real? Only these 2 are imaginary and the rest are all real. Okay, real. Now out of them, this and this, they basically corresponds to surface effects and rest correspond to entire volume effects. Okay, so this is what the empirical optical model and the origin of the various terms are all about. Now previously we have talked about the experimental observations which match nicely. Now this time what I am showing you is basically the differential scattering cross section, or basically the angular distribution I am showing. So here basically we have the angular distribution of 17 MeV protons from nuclei with Z approximately 26 to 30, in this range. Now, the solid lines are theory. So, solid lines are theory, and the dot 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 are experiment. So, you see how theory nicely represents the experiment. And remember, for this calculation, all the 5 terms that we have previously shown, they have been used. Now, you might say, okay, very good. So, optical model is brilliant. However, you have to say, I must say this, is that it also has basically limited set of adjustable parameters, and so is not capable to describe abrupt variations in cross section, say for example, which happens in the case of isolated resonances. However, in spite of this limitation, it can give us a good description of the cross sections in presence of the oscillations of large width in the continuous region. Basically, it treats these as wave phenomena. Of course, these are basically wave features. So, you are asking me, how is this happening? Basically, sometimes very simple things also work. The entire idea was to use a mean field sort of potential to describe the individual interactions of nucleon between projectile and target, right? So what was our aim? Basically, the aim of optical model is to find a potential to describe the smooth variations of the scattering cross section. This was our aim, remember. Basically, to describe the smooth variation of the scattering cross section as a function of, number 1, the energy of the projectile, and also number 2, as a function of the target nucleon mass number A. So this was our original aim. And we have been very successful with our basic assumption, because you see, the general situation of scattering is very complex. However, in spite of this complexity, great simplification has been obtained if we are interested only in the average properties. This is very important. Here we are talking about average stuff. Which are average properties, again, which are away from resonances and states that strongly get excited by direct reaction. So our basic idea is very similar to the mean field approach of shell model. বোঝা যাচ্ছে? What was the complexity and how we have approached this problem? See the curves over here. I have basically used the same set of parameters in these 5 different potentials, same set of parameters to describe this particular Z from 26 to 30. So for all these 5 nuclei, I have used the same set of parameters, and we have found remarkable agreement. Don't you think this is a very unique feature of this model? So basically, I have talked about the basic origin ideas for all these 5 terms. Okay, you have to remember that the origin of optical model potential. Now, this part, the first part of our lecture was basically introduction to the concept of optical model, right? Now you have to understand that here we are basically talking about the phenomenological optical model potential. This is what I am talking about. So basically this is not microscopic in nature. I am just putting by hand. However, even though I am putting by hand, look at the beautiful reproduction of theory with data. So this means there is great value even in such phenomenological behavior. So you have to understand that our origin of this optical model potential is the interaction between nucleons in the projectile and the target. Now again, তোমরা যদি বলো, of course in principle it is possible to calculate the potential from a nucleon interaction. So basically what I am saying is that optical model, this basically concept of writing in terms of potential as real plus imaginary part, okay, this we can do from microscopic calculations as well, starting from your NN calculations, nucleon potential incorporate. This will be very hard to do, remember, very complex. Another very simple way is from the basic features of the nuclear physics, nuclear interactions, target, projectile, their behavior, we can do a phenomenological approach. We can do that. So we will get a phenomenological approach here where we will put the V various terms, and these are the 5 terms that we have discussed. This is basically we have put by hand. This is not a microscopic approach. This one is a microscopic approach, whereas this one is the phenomenological approach. See, again let me again review the various terms. So the first term VR, basically we have chosen the dependence. See FR, why was the dependence chosen? This dependence of Wood section potential was chosen so that basically this potential basically closely follow the nucleon distribution, right? So this was chosen so that because we expect a radial dependence like this, because this potential will now closely follow the nucleon distribution in nucleus, and this is known as, basically I have told you, Wood section form. Again, see, we have introduced the Coulomb term here, right? This was the Coulomb term. Basically this was introduced mainly for charged particle, for considering the charged particle scattering. Yeah, before I finish, I must say I have not told you about the number of adjustable parameters. There are a large number of adjustable parameters that you have to adjust while fitting the data. See, for fitting this particular set of experimental data, you need a large number of parameters. See here, say for example this one, WD, again R, say capital R, small a. There are lots of adjustable parameters, and again we have to fit them properly to get to match the experimental data. Again, they will somewhat dependent on the range of nuclei chosen. Now, before I finish, let me finally show you this Wood section form. On your request, I am showing this to you. The difference between the introduction of this F and this DFDR. How do they affect? Now you see, this is the F. I am not showing the full part, only the part near the edge is shown. You see this round smooth border. This is very much closer in reality than that of square wave. Also, the diffusiveness parameter here, this basically decides this region where F changes from this 0 to 1. Okay, now what about this DFDR or F prime? So see, this DFDR is very much prominent, or this value is quite large near the surface, and that's why we have included this in the spin orbit term. to consider the polarization effects. Again, I told you that this DFDR is basically acts as a surface effect. Why? Because we know that low energy, that is at lower energies, there are no available unoccupied states for the nucleons inside the nucleus, and so the interactions will be basically with the surface, and this is why this is surface absorption effect is basically important for low energy projectiles. Okay, so before I conclude my talk today, let me summarize. So we have covered lots of topics in our this 2-lecture class. We have first started with the motivation. I have shown you the data for global cross-section studies. So motivation for studying the optical model. Later on we talked about the basic assumption of mean field and then the similarity with the shell model. Afterwards we talked about the importance of the imaginary potential, and so we started with the square wave application of a complex potential and then showed the importance of how the basically absorption arises because of this imaginary potential. We showed this. Next we did a derivation of expressions for reaction and scattering cross sections for high energy neutron interactions with the nucleus. After that, in the second class, we discussed about the fact that we have already talked about the nuclear reaction estimation of cross section through partial wave analysis, and optical model is yet another way to approach this problem of understanding the cross sections for reactions, basically absorptions. And finally we talked about the phenomenological optical model and its 5 important terms, including the various adjustable parameters. We have excluded the microscopic optical model discussion for our talk today. That's it.